So welcome to another Newton's law problem. So in this case, we have this past paper problem. We took it from this paper right here. I took a screenshot of it. You can find it online by just searching physical sciences past papers. Okay, this is from the Gert Sibande District, and yeah, it was Feb of 2023. I'm assuming this was a test. Okay, so this was the question that was mainly dealing with Newton's laws. There's another one after this. I just took this first part and then we'll get to the other second part of it after we're done with this one. Okay, so let's get to it. Right, we have this block, simple block, and then a constant force of 40 N being applied to this 6 kilogram block. Okay, and then now this block accelerates to the left. Okay, now let's note the keywords that are available in this problem statement. We are given the mass and we are told the force. Then there's another thing that's a keyword that we need to acknowledge, this rough surface. Rough surface means friction is present. Remember what they say if friction is not present, or if friction is so small that we can neglect it. They usually use keywords like treat friction as negligible or neglect the effects of friction. That's when you know that, okay, I shouldn't worry about friction. But in this case, they said rough surface, so we have to account or include friction in our calculations. So already in your mind, you should be ready for that. Accelerates to the left. Now we have our sense of direction. Okay, so those are the key things that we have. The statement then continues to say the kinetic frictional force between the surface and the box is 22 newtons. Okay, remember there's a difference between the static friction and the kinetic frictional force. The static friction is that which acts on the object when the object is not moving. It's basically trying as much as possible to make sure that the object is not moving. So if you then apply a force that's greater than this force, it will start moving. That object will start moving. As soon as it starts moving, static friction stops and kinetic friction begins, because the nature of the two is different, right? Kinetic friction is a result of two surfaces sliding against each other during motion. There's a relative movement between the object and the surface onto which it's moving. And then static friction, on the other hand, is dependent on the normal force of the object and some other force components depending on the situation that you have, right? And as a result, it only works if the object is not moving at all. But that's for another question. Now, for this case, we'll just focus on the kinetic frictional force. And then we have 2.1. State Newton's first law of motion. So this is a type of question that you usually use the definition that you have memorized from your notes and so on. You have to write it as it is, okay? Don't miss any keywords. That's why it's just better to memorize it. But obviously, you have to also understand what it means practically. So usually what we say for this first law of motion, we say, well, a body will remain at rest, or it will remain stationary, or at constant velocity unless a non-zero net force acts on it. Okay, depends which one you choose, but let me write it for you. Unless a non-zero force acts on it, non-zero net force, actually, not just any force. So you must say net force. So some textbooks or some definition, they would say something like a body will remain at a state of rest unless acted or unless a non-zero net force or unbalanced force, or unless it is acted upon by an unbalanced force, right? Some use the unbalanced keyword, some use the non-zero net force keyword. Depends which one your teachers recommend, okay? But usually they all mean the same thing, and the keywords must always be there. Non-zero net force, remain at rest right? So that's what you must always make sure you include in your definition. Otherwise, we don't know where you took that definition from. So now, that's what the law says. Then we go to 2.2. Calculate the magnitude of the acceleration of the box. So we are told that this thing accelerates to the left after the 40 Newton force has been applied to it. So what that means is we can sum our forces, Fnet, and this should be equal to the mass of the block times its acceleration to the left. And we are asked to find the acceleration, okay? So let's choose direction. I will choose to the left because this block is moving to the left. So it's convenient for me to choose the left as positive. You can choose right, it's up to you. Okay, I just don't want to mess up with my acceleration, and it makes the whole thing algebraically messy. And it's inconvenient for me because I can forget those type of things when I'm substituting. But any direction, as long as you will remember all the necessary things that you must do. Now, let's sum these forces. You have the 40N going to the left, so it's positive. You have the kinetic frictional force. So if you draw your free body, actually we were supposed to draw it before we even started. Let me do this. This block will have normal force, weight, and there's a 40N force acting that way. And remember, frictional force always acts opposite to the direction of motion, so it will act that way. The 22 newtons that we're given here. Right, so that's what happens. So since it's acting to the right and we chose left as positive, therefore our 22 will be negative when we substitute. And then now we have our mass is what is 6 kilograms, and then we're looking for A, so we don't know A. From here you can simply divide both sides by 6, so you'll get A being 18 over 6. This is 3 meters per square second. That's your acceleration, and it's constant, okay, which makes sense. So this law is Newton's second law. Right, that's how you would solve 2.2. It's a simple 3 marks. If you wanted to, because some people would like that step, you could have added this. You could have added the first step where you sum these forces. Let's say you call FA, which is the applied force, plus minus your FK, which is your kinetic frictional force. Then you would have said this is equals to MA. I skipped it because I already had the values. So, but if you want, you can start here and then substitute. It's all up to you, okay? So now let's move to the second part of this question. So in the second part of our question, we're given this block. And then it's hanging, or it's connected to a hanging mass, which is 8 kilograms. And then they are connected by this light inextensible string, okay, running over a frictionless pulley. So we are given another piece of information that the kinetic frictional force between the 6 kilogram block and the surface is 7.64 newtons. You know, some clues or some keywords in a problem statement, they sort of hint you to what's happening in the system. So as soon as you see kinetic frictional force, you must ultimately assume that this thing is moving, this system is moving. So the 8 kg block will likely be moving downwards, and as it moves downwards, it pulls the 6 kilogram block that way. So this whole system is moving, okay? Even though they didn't tell us explicitly, but they said kinetic frictional force, then we can sort of deduce that this thing is moving. It has to be moving because kinetic frictional force only works for moving objects. Right, so now we're asked to draw the free body diagram of all the forces acting on the 8 kilogram block. So we know that as soon as you see a string that is being pulled either by a force or that has a weight being attached to it and is hanging, excuse me, it means there will be tension. So this is the 8 kilogram block, and up there we have tension, and down we have the weight of the block. Some call it FG. It's up to you, whatever you've been taught. I just prefer W. Okay, so notice that my arrow for the weight is longer than my arrow for tension. Why? Because weight is greater than tension in this case. Weight is pulling the block downwards and the block moves downwards, which means the weight of this 8 kilogram block, or the gravitational force of the 8 kilogram block, is greater than the tension on the string. So that's why it's able to move downwards. If they were equal, it would not move at all. Right, so that's why even in the free body diagram, I made sure that I represent that. It shows that you understand what you're doing. Okay, you're not just doing things out of habits or whatever, or not understanding what they are actually. 2.3.2, the magnitude of the acceleration of the 6 kilogram block. So there are two ways of dealing with this problem. Okay, it's either you do the free body diagram of the 6 kilogram block, you solve using Newton's second law, and then you move to the 8 kilogram block, you solve using Newton's second law, and you'll have two equations and then you'll solve simultaneously. Or you combine the whole thing and just solve. Right, let's start with method 1. So we already have the free body diagram for the 6 kilogram block. What about the 8 kilogram block? Oh yes, we have the 8 kilogram block. Let's check the 6 kilogram block. 6 kilogram block, we would have N, we would have weight, we would have the tension, and then we would have kinetic friction. Usually it's small f and a k, like this, small k, subscript k. All right, so we have that. This is for block, the 6 kilogram block. So then let's start the first method, method 1. We call it method 1. So for 6 kilogram block, I choose to the right as positive, because I know the 6 kilogram block will move to the right as the 8 kilogram block moves downwards. And then I sum my forces. I say, well, right is positive. You can also write it in words. I just prefer the symbol. Then I say, therefore, my Fnet is MA. Right, now tension will be positive, but the kinetic friction will be negative. Then I have my MA. Then from here, I can sub in my values, right? So I don't know tension, so I'll just make it the subject of the formula, which means I'll have something like this, MA, because I will essentially transpose this guy to the transpose, right? Then I'll have plus FK. And then I'll substitute and solve for T. So since there are two unknowns, this is ultimately now an equation. I can call it my equation 1. Okay, so let's go to the 8 kilogram block. It's going downwards, so I'll just choose downwards as positive. Right, and I'll say Fnet is MA. From here, I know I have tension, which is upwards, and therefore it has to be negative, plus the weight, which is downwards, and therefore it's positive, MA. A is moving downwards, so I'll just leave it as positive. Okay, and we can make T subject as well. This means T will be equals to W minus MA. You can do this step by step. I just skipped a lot of steps to save time. But notice that the negative disappeared. I multiplied by negative both sides, and then I moved the W that side. Then now you'll have mg minus ma. Mg is 8 times 9.81, sorry, 9.8 minus and then 8 times a. Therefore T is, no, not therefore. And then now notice that we have two equations. This is my equation 2. So I can equate them and solve for A. So because T is equal for both blocks. So I can say equation 1 is equals to equation 2. So now we're solving simultaneously. So that means we'll have 6A plus 7.64 being equal to the other equation, which is 74 point something minus 8A. Sorry, I meant 78.4 minus 8A. Yes. So if you know your maths, here we just solve for A. First, we'll say plus 8A, so that it cancels out with this A. And what we do that side, we do on this side. And we'll add plus 8A here as well. Right, and then we solve. Right, from here onward, it's just maths. You can say A is, it's simply 70.76 divided by 14, and then you punch your calculator. I get 5.05 meters per square second. Per second squared, I mean. It's the same thing, but whichever one you prefer. Okay, so you get this as your final answer. So that's how you would solve for a question like this using method 1. Most people prefer method 1 because it's sort of easy to conceptualize. But let me show you method 2 quickly. I will move quicker because most people don't like method 2 really. So here's how it works, right? So for method 2, you would have to ignore the tension. And then you only focus on the forces that contribute to the motion of the system. Okay, so what does that mean? It means, what is the main driving force of the system? What's causing the system to move? It's the weight of the 8-kilogram block. Okay, and then what's opposing this motion is the friction as a result of the 6-kilogram block being placed or resting, not resting, but rather being placed on top of a surface, which is the table in this case. So, and then you'd have to you'd have to consider the overall mass of the system. Usually it works for all systems where 2 blocks or 2 objects are connected by a string, right? I'll show you in another example in a different past paper problem. So what you have is something like this. You still say Fnet is equals to MA. I say you ignore the tension, but you don't actually ignore it, because what happens is if you combine the free body diagrams of these 2 objects, the tension vector components, this one and that one, they are going in opposite directions, so they will tend to cancel. And then if you were to have a combined system free body diagram, it wouldn't be in that free body diagram because these two components would cancel, right? And then you'll only be left with the weight of the 8 kilogram object and the frictional force contributing to the overall motion. And then the overall mass of the system will be 8 plus 6, right? You will get it on, there's an example where two blocks are being pulled on a surface. I will show you in our next video. So that will be a bit more clearer. But it's the same concept. It's just that now one is hanging and the other one is on the surface, but it's always the same concept. And then what you do here is you choose a direction of motion. So you imagine that these blocks are connected like this. If I choose that way, right, as my direction of motion, remember, downwards is also still positive. So if I choose right as positive, it ultimately means my downwards is also positive, right? Because the 8 kilogram block is actually moving downwards, which ultimately causes the 6 kilogram block to move to the right. Right, so what then happens is, let's choose this side. What then happens is, it means our frictional force, the kinetic friction, is negative, plus our weight for the 8 kilogram block, plus our total mass of the system, let's call it mt, times our acceleration, right? And then you would say minus, now we substitute, I think it's 7.64, yes, plus the weight of the 8 kilogram block, which is the main driving force causing the system to move, 9.8, is equals to the overall mass of the system is 8 plus 6 times A. Okay, and then you'll find that this will be 70.76 is equals to 14A. Then you divide both sides by 14, and A is still 5.05 meters per second. So both these methods work, just that method 2 is way simpler. Once you understand it, you will never go and solve for systems connected by a string, two blocks, right, connected by a string using method 1, because method 1 takes forever. Method 2 is just 1, 2, 3, 4 steps, right? So that's the main difference, okay? And then I will highlight it again on another problem. That even for problems like this where you have two blocks, there's an angle here, and then there's a force being applied here, and these blocks are connected by this string, it still works. This is block A, this is block B. It still works. It's the same concept, because that's what happens when two objects are connected by a string. Okay, so yeah, this is how you would typically answer a question like this one. So thank you very much. I'll catch you on our next video.